In mathematics, there are some great theorems and proofs and derivations, most of which people take for granted without either being familiar with or understanding how they were derived. Now, I'm going to call them math's big four. You have first the Pythagorean Theorem, where on a right-angled triangle, the side opposite that right angle, called the hypotenuse, happens to be always the square of the sum of the other squares. The second one is the Quadratic Equation, and there's a solution to it. The third one is pi, the computation for the circumference of a circle. And the fourth is E, a magical transcendental number that allows you to do, among other things, instantaneous compounding. Starting with the first one, a right-angled triangle, and I should note the Chinese have a different proof preceding that of Pythagoras, and let's label the two legs next to the right angle, x and y, and the hypotenuse, that's the side opposite. What a strange name. We're going to label z. And, well, first of all, we can lay this out squaring each of those three sides. And then if one completes the box surrounding the third side squared, which would be here z times z, well, it must be the case that the x and y are the sum of each of those sides. And, well, let's see. We got x and y, half of them, but there's 4 of each and every one of them. So let's see what that is equivalent to. And what it's equivalent to is a box of the same size, the same dimensions, but now we note that, well, you have y times y, that's y squared, and you have an x times x, x squared, and the other two boxes that are the remainder are x times y, but if they were both equivalent and you add them up, well, then you have 2 of the xy's, but 4 of the half of xy's, which, if you will, cancel, subtract out, leaving the remainder, which is z squared, equals the sum of y squared plus x squared. Pretty nifty, eh? For pi, the computation of the circumference of a circle, your first approximation would be maybe to attempt to put a box in it, a square, which would have 4 sides. And, well, we want to make a better approximation by making a piece fit in that portion that makes it closer to the edge of the circle. And, well, there's 4 pieces there. That makes sense. And what you would do is you would add the better approximation, subtract the lesser approximation, which turns out it's the infamous summation of 4 divided by 4 times your index counter minus 3. Then you're eliminating the portion you're subtracting for the portion that's less approximate, which is, again, 4 times your divided by 4 times the index counter minus 1. And you just keep adding that up and you get pi. 3.14159, etc.
Here, let me show you. It's 4 divided by 1 minus 4 divided by 3 plus 4 divided by 5 minus 4 divided by 7 plus 4 divided by 9, etc. minus 4 divided by 11, and so on, and so on.
And for the quadratic equation, which gets its name from quadrangle square, if you like, you have 3 terms, one of which is squared, one of which is to the first power, and then one of which actually is to the 0 power, because x to the 0 power is 1. And you can label these for their coefficients a, b, and c. So if you take the equation, multiply it times 4a, you get the next line, and then if you add plus b squared, but subtract out minus 4ac, you get the next line, and then you can factor that, so you get the factors of the 2ax plus b, squared if you like, equals the right-hand side, and take the square root of that, because you have it factored out as a square, and then you subtract minus b, and then there you go, and we finally divide by 2a, and you get the solution to the quadratic equation. Minus b plus or minus the square root of b squared minus 4ac divided by 2a. Last but not least is e. And first I'll do the computation, and then we'll talk about its significance. You have something called a factorial. That's times itself declining toward 1. And if you do those sequentially, and then you compute the reciprocal of those factorials, and then add those all up, then you'll get e. So here's our index in column A, and then b is the factorial of that number in column A. So, okay, 1, 2 times 1 is 2, 3 times 2 times 1 is 6, then the next one is times 4, rest of the same, gives you 24, etc. Take the reciprocal of those, divide it into 1, that's column C, and we add them all up. We get D, and guess what? 2.71828. That number is kind of called the transcendental number. And E had a lot of uses, especially before calculators and computers and logarithms. Oh boy. But in any case, it also has a use in finance in terms of compounding. You might have a future value, and if you compounded it once a year, the rate of return as a decimal, 1 period, that's the P here, for T time periods, well, many times it's compounded maybe quarterly, maybe monthly, like for a mortgage, credit card. P in this case, the frequency would be 12. By the way, there's a little shortcut for yearly compounding. If the amount doubles, it satisfies the equation with R now as a percent times the time period, years if you like. The product will always equal 72 if it doubles. Nice shortcut. In any case, if you increase the frequency, now let's say from yearly to quarterly to monthly to daily to instantaneously, it turns out the future value will equal that value of E to the RT power, where R is again a decimal. That's really kind of nifty. So we got an idea of where the Pythagorean Theorem came from, how you solve a quadratic equation, and these two so-called transcendental numbers, because you can't really make them into a proper fraction. By the way, if you don't want to have to memorize them, which also means if you don't do enough digits, they're not quite exactly correctly accurate, there's a ability in Excel to use a reserved word to call them back, pi with the brackets, and exponent for the number 1, which gives you back e. Pretty nifty stuff.